So now we will talk about one of the classical algorithms for clustering, which is called k-means, which is, I would say, the reference algorithm somehow in the field. So k-means, in k-means, we are calculating the optimum reconstruction error according to MI. So we know that it is impossible, analytically speaking. We cannot develop the equation to get with an exact solution upfront when we are dealing with the reconstruction error, because we have some kind of chicken and egg problem. At first, we are determining the position of the centers MI, which is what we are looking to find. What is the right MI to use, the right values for MI. This depends on the labels BIT. So we are using this kind of assignments to BIT, that is assigning data XT to center MI. And the other way around, with the choice of this BIT depends on the position of the center's MI. So MI depends on BIT and BIT depends on MI. So we are not able to get this solved directly with directly with an equation. So we should proceed into some kind of iterative resolution. So we will make successive approximation of BIT and MI, and over time, the algorithm, by setting up, I would say, BIT at the next step from the current MI, and then we estimate MI from the new BIT. We will repeat this many times until we converge to some kind of solution, and often, it converges to the right solution. So we will make a good partitioning, a good clustering of the data, and setting up the MI properly such that the BIT will be fine, and the overall reconstruction loss will be minimized. And so this is repeated until convergence, when we see that we reach a stable state or depletion of resources. So now the question is, how can we estimate the center's BMI according to the label BIT? So this is kind of straightforward. We will rely on the partial derivative of the error criterion, which is here the reconstruction error criterion, according to MJ. That means that we are looking to say, okay, we are making the derivative according to some given MJ. So MJ is one of these centers. I would say when we get the reconstruction error, the derivative of the reconstruction error according to MJ equal to 0 over all MI from 1 to K. So we are looking at the reconstruction error criterion, which is the one here that we saw before, and we set that to 0. And by solving this, we are able to say, okay, yeah, the right value is this one, minus 2 summation over BIT xt minus MGT is equal to 0. And just by solving this around, we are getting this equation. MJ is equal to the sum over all samples T, BGT xt. So remember that BGT is set to 1 only when data xt is assigned to center MJ. So we are summing over all T's, but only the xt which are assigned to MJ are used here. The others are multiplied by 0, so they are disabled, so they are not used here. And we are dividing by the sum of BGJT, which is basically the sum of samples assigned to MJ. And if you look at this carefully, basically, this is the usual way to compute the mean, the average of some values. By including BGTs somehow to pick up the ones in the full data sets that are assigned to MJ, and we are looking at the means of these samples that are assigned to MJ. So no big deal here. So with the partial derivative set to 0, we are kind of finding the analytical equation to compute the new MJ. But this is based on the current assignment, the current partitioning made reflected by the BIT, BJT. So the algorithm goes that way. So basically, we set up the centers MI randomly. So we are assigning them to random values. There are different ways to do that. We will see that later. And as long as the stop criterion is not reached, we are estimating the data labels according to the position of the centers. So first thing is to look at which center is assigned every xt, looking at the minimum distance, Euclidean distance often. This for all centers and all samples. So we've got the BIT for everything, for the across the centers and the samples. Then from these BIT, which are based on the current MI, MG, we will reevaluate the MI according to the new labels. So we are updating the labels through BIT. Then we will update the centers from the BIT, and we get this through a usual mean. And we are repeating this. So new BIT, new MI, new BIT, new MI, and so on, until we converge. Sometimes what we see with k-means, it's that it's a relatively stable algorithm. It will converge up after several iterations, and we'll just stop changing. So because there is no change, we could just simply stop it there. And in the end, we are returning the center's value MI, which are the values we are looking for, basically, to do our, for example, our vector quantization. So to illustrate this, we have this kind of figure. So we see here on the top left here that we have about 4 clusters. We can see in these gray dots that seems to be organized around 4 clusters. And then we are initializing. So these are the black dots at the second step here, C1, C2, C3, C4. So these are the initial means. So the centers somehow of our algorithms initialize in some random ways. And then from these random initialization, we are assigning. So we see here at the second step, the fact that we are assigning all samples to the nearest center. So they are linked here. They have an edge from their position to the new center. So we see how it is done. And from this assignment, we are reevaluating the new means. And we see that these mean vectors are moving somehow. For example, we see C3 that moves quite a lot from, I would say, from here to there. It moves down a little. C2 move also quite a lot from down right. C1 a little on the down. And C4 hasn't moved that much. Basically, I think it stayed the same because there's no changes in its assignment. Now, if we go with the second step, same thing, we are reassigning and reevaluating the mean points. You see that still things are moving. The assignment is changing somehow because for example, with C4, we see that this sample here has been reassigned from C4 to C2. That means that C4 will move down and C2 will move also a little down, and so on. And eventually, we are repeating this at step 3, same thing. And at step 4, we are done. Basically, in this setting, things are not moving anymore. So we are not changing the assignment. The BIT are not changing according to the new means. So the means are not changing either. Also, so we see a convergence at the 4th step. Now the question with k-means is how can we initialize and stop the algorithm? So different ways to initialize the center's MI. The first one is to randomly select k instances of x. So basically we pick up k random values of x and we use that as the initial centers. The other way around, so the first one is kind of the basic approach. It works well, but we can be unlucky. We can be there can be some bad lucks in the choice of the k instances. That means that it's not necessarily always very robust in terms of approach, but that's the basic way of doing this. We can also calculate the mean vector for all the data and initialize k centers around this mean, but having for each centers a slight variation, random variations. That means that we pick up the global mean and we set the specific k means around that global mean, close to that global mean. And quickly they will move around. They will just kind of spread toward the different data that are maybe further away from the center, from the mean, the global mean. A third approach is slightly more complex. It is based on the use of the principal component, the directions where we have the maximum variance in our data. So basically, it means to calculate the principal component of a data set. So we have one direction that is direction of the maximum variance according to a multivariate Gaussian distribution. And then we project all the data to that line. So we just map everything on that line corresponding to the principal component. And then we split in equal size K groups. So we just say, for example, if we have 10 samples and we split that into, I would say, 5 groups, we have like the 2 first for group 1, the 2 second, the 2 next for group 2, the 2 next for group 3, and so on. So we will have 5 different groups of 2 data each. And so this assignment is made there. So this is used to compute the BIT. And from this BIT, we go back in the original space. We forget about the principal component. We have made the assignment BIT. So we are able from that to estimate the centers, the corresponding means for each group. And we have the MI from that. And these are the starting point MI that we will use for our algorithm. So these 4 approaches are basic approaches. The simplest one is the first one. The second one makes sense and works relatively well. So the third one is more complex, but it can give some advantages in some cases. But now we need to stop the criteria. And so the first stop criterion we are using is to use a maximum number of iterations. That's required because we can see sometimes a really slow convergence, especially for big data sets. So we may require to stop the algorithm at some point. But usually K-means is not going through, unless we have very small number of iterations allowed, it's not going through all resources available. It converges to some solutions. And as such, we can maybe simplify also, or not simplify, but get a slightly more sophisticated approach by looking at the variation of the position of the centers. And if these variations are below a given threshold, we just say, okay, that's it. We don't see enough changes. We will stop the algorithm at that point. A thing with the K-means is that we don't have any guarantee of convergence toward the global optimum. You know, we are not sure it will converge to the global solution. The outcome depends on the choice of the initial positions of the centers. So basically, with different choices, we can get into some local optima that may be significantly poorer, worse than the global solution. And there's no big ways to ensure that we will get the optimal solution. However, we know that K-means is converging relatively fast. You know, it takes several iterations, but it gets into a stable configuration quite often. And so the algorithm will stop there. And well, we need to fix in advance the number of centers. So this is a big deal somehow, because we may not know in all cases how many groups we have in our data set. But with K-means, we need to figure this out, or at least put some possible K values and use it. So if we have a good knowledge of the data at end, we can be quite natural to set up this. For example, with the color map, it's not that we know in advance the number of group required. It's that our modeling imposed that we have 256 different means, different colors that we can use. So if we don't know anything about that, we may just empirically estimate K. We just make tests with different values of Ks, and we look at the results to pick up the best value. There are even modifications to K-means with algorithms like the leader cluster algorithm. So the point is that we are incrementally add new centers as we see that the distance of data to its center exceed the threshold. When we have data to a given cluster that is too far away from the center, we just, okay, yeah, let's split this. Let's set these data, let's assign it to a new cluster center. So we will increase the value of K. Or a variation over that is to do the other way around, is to split or add a center when we see that there are too many samples in a given cluster. We can say, okay, over, I don't know, 1,000 samples in the cluster, we split that into to get 500, and because we probably want to limit the number of really big clusters, because that means sometimes that we have huge clusters with possibly much smaller ones that are on the side, and this maybe the big one is not capturing well the thing, is capturing many things together. So an example of k-means into groups, we can see here like the first partitioning. So we have in fact here some kind of labels that are given here, but we are not using them for our example. So that iteration one, we are looking at just to set the centers as the white dots here, and the partitioning is made according to the yellow line, which is corresponding to the line of equal distance between the two white dots. And so according to the size of each size, we are making the partitioning. And quickly we see that there is a big change here. You know, the centers are moving really closer to the frontiers because the density of the data is there. So the two centers has moved significantly toward that way. And then we are re-evaluating the partitioning. We see here that it tends to move a little down left for the top one and top right for the other one. And that continues somehow here, here, up to even I would say there. So notice move requires 7 iterations. The first one was big, the other ones was much smaller, but still the results is interesting because we can see the split, and the split is in fact making some sense here according to the ground truth label. So even though we are not using clustering for doing classification, we can use label samples as a way to check whether or not the algorithm is working well. So another example, this time with 3 groups. So we can see somehow the labeling of the data beforehand that is not used for our example. And we have these 3 centers. We see that things are moving that way. The centers are moving with a different shape, and we get into a different split of the dataset quite quickly. And over time, you know, we need to look at this, the trajectory. It moves a lot, so we can see the whole trajectory here. And so we get into something that makes sense in that place. And if we look at this here, yeah, it's kind of seems to be a good configuration. And in terms of classifications, it seems to be working well, even though we are not trying to do classification with that. The labels kind of confirm that the clustering done here makes sense. So if we go back to the color map compression application, where, you know, we just use a fixed number of colors to color every samples and assign the samples according to the index in the color map, we can see some results. You know, the original image is here. So basically a bunch of MAMs of different colors. And then if we just use, for example, 2 colors, so we get into this kind of brown and green modeling with not much details. We don't see much things, but it seems to be still, can guess some of it. But, you know, with 2 colors, it's difficult to do anything right. With 4 colors, it's better, even though it's not perfect. With 6, it starts to make sense. You know, with only 6 colors, of course, there are some artifacts in terms of the colors, but it's kind of recognizable. You know, we can understand what's going on. With then with 10 clusters and different colors, it's even better. And then we see the original image. So of course, the compression here is kind of heavy. You know, using only 10 colors for compressing an image lead us to really a loss of information that is significant.